You But it's because of my channel got demonetized lately, a couple of weeks ago, and the reason that YouTube gave me was that my material in my channel.
Is that a dead? Hold.
I've been married a long time ago. What year to go? What year to come from?
I can't. Get out of here.
Married a long time ago. What year to go? What year to come from?
You see what I mean? These mods, man. How could I not be so giggly all the time when that's what I hear? When this is what I deal with on a regular basis? There's this good meme too. Good meme. All right,
Nice
come on.
Meme.
What?
Combo combo.
Jeez. Okay.
Okay.
Don't tell me I just said okay and it said
Okay.
That's right. Get no scoped. Get no scoped.
no scoped. Classic.
Congratulations, you won.
Thanks.
Boom headshot. Combo combo.
Hi, Billy Mays here for OxyClean, the stain specialist.
Billy Mays.
It's over 9,000.
Do a barrel roll. Do a barrel roll. Oh, and the Oscar goes to me. I got the Oscar. Wow. Wow. This doesn't do anything else, does it? This is completely useless. This is it's just an Oscar. All right. No, wait, no. I laughed at myself. Oh, I laughed at myself. Okay, that has to count. I guess that has to count. Dang it, man.
And we'll suicide nearly triple the amount. But you gotta call now.
I'm just gonna throw a bunch of them down, and we're just gonna see what happens here. What else can I get that just appears?
Do you know that way?
Okay, all right, that's so dumb. Oh my gosh. All right, fine. It got me. It got me. I don't even think I've seen everything that this mod has to offer. This is an insane mod. This is so insane. Look at all these things. Saxophone. All right, we need to move on. That's enough of that. I'm moving on. I'm moving on from that one. Whew. Oh my gosh, this is a wild video. This is so much. That was a good one. That was a good one. A reference to the Beat movie. This could be the end of me. World where I lost a life. We're gonna see if I lose another one. All right, meme in a bottle. Oh my gosh. Splash meme in a bottle. Memes will rise from where this bottle lands. You might want to find out how to make more effective. Wherever it lands, it'll summon multiple memes. All right, we'll keep that one. Sunglasses, deal with it. Can I put these on? I probably can't put that in for the sake of copyright, but oh yeah. All right, let's see what happens. Splash bottle of meme, here we go.
Chocolate! 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 Chocolate!
Gosh.
Chocolate!
Wow. Woo! Chocolate. Chocolate. All right, what's next?
Charlie. Charlie bit me.
It's a good meme, too. Good meme. All right, come on.
Meme.
It doesn't count. I wasn't in the mod. This is, I wonder where the Narfi structure, where could it be? Where could it be? Okay, can I like get in somehow? There's a lot of shulker boxes. Can I like, I guess I'm going up. I went up my leg and I found a lot of me up there.
Breaking Minecraft.
Whoa. Oh my gosh! It's me! It's me! It's just my voice too! That's insane! That's insane! That's insane! You just get close.
With your dumb ideas. Breaking
Minecraft
with your dumb ideas.
Okay, alright. You guys are so loud. I'm so loud. Dang it. I don't know. I'm just gonna turn down the master mode. Hey, Conrad, for this 1.12, super old. Why am I'm on an island. All right, we're going this way. Apparently to get this one started, this is also an island? Apparently to get this one started, you need a notebook. How do I... Time we've done that. This is the second time for this. Snare one. Do a bass note. Can I like... How do you pick it up? What if I get multiple? Ooh. Ooh. What is happening right now? How do I give you a different instrument? Whoa, open MIDI folder. Bro, you can like, whoa. Oh my gosh, there's so many. All-star, upload and play selected. Oh, you can pause them. You can pause them. Despacito. Oh my gosh. How do I give you a different instrument? Okay, I'm confused. All right, joining world, loading terrain. Oh. Wow, that is not at all what I expected to see when I first logged into this. Oh my gosh, the leaves are Murphy should.
You should always gamble. You should always gamble. When the odds are stacked in your favor, which inside any casino is...
The GMTK Game Jam is back for 2026. This is a rapid-fire game-making challenge where you have to design and develop a video game in just 4 days, or 96 hours. and that game must fit a theme, which will be revealed when the jam begins on July 22nd. The jam will run until July 26th, at which point everyone will play and rate the games so we can find the community's favourite entries. Oh, and I'll also play a bunch of those top-rated games myself and pick my favourites for a video on Game Maker's Toolkit. Now, a game jam is a great way to flex your creative muscles, to take a break from that big project you're working on, to find new friends and collaborators, or perhaps to make a prototype for your next big release. That's what happened for the creators of the 2021 jam entry Tethergeist, which just came out on Steam and Switch as a fully fledged game. Congratulations to them. This will be the 10th GMTK Game Jam, so I just wanted to give a huge and heartfelt thank you to the thousands of people who have participated in the previous jams, and I hope to see you at this big anniversary event. All of the details can be found on the itch.io page, including the jam date in your local time, our rules on using AI, our community-run Team Finder website, and once we get closer to the jam, an invitation to our Discord channel, where you can chat with fellow jammers. Okay, that's all from me. Join the jam on Itch, and I'll see you in July for GMTK Game Jam 2026.
Boy, oh boy, do I want a super painful, searing headache right now. That would just make my day. Do I want a super painful, searing headache right now? That would just make my day. Alright, I'm gonna go throw up now. Oh, this just hurts your eyes. This really does just hurt your— oh, no. Oh, this lava looks like it's flowing. Why is it flowing? This is the Scrolling Textures resource pack, and sure, it's not a mod, but good God, is it annoying. This body of water is moving, even though it's not actually moving. It does this to, like, everything. If I zoom into the distance, even those textures are moving. I think the thing that makes this even more annoying is that the mob textures don't. They're just fine, but everything around them just scrolls past. Oh gosh, that's even more annoying. This pack is made for 1.16, so there are a few blocks that it didn't really catch. Also, it's using the old coal and iron textures, but just add it to the annoying list. I think the most egregious part of this is when you open your inventory because everything just moves. Oh my gosh, even the fences. Look at— oh no. Look at the flowers. The flowers are moving too. There's like 4 of them. What in the world? Oh no, the torches too. Look at that. Oh gosh, what's happening there? Why is there just a gray stripe? Oh my gosh, the bookshelves, dude. Oh, they don't. The side textures are affected by another resource pack of mine, I guess. Oh, that's weird. But the top of it moves. Well, that's annoying. This is just so excessive. Like, what in the world? Oh my god. Oh no. Oh gosh, this is just so much. Oh, look at the kelp. Oh no. Oh no, it's moving the opposite direction of the gravel. What is going on? Oh, this is so— my brain just doesn't know what to do with this information.
got no future.
Narf. Say you want to drive from New York to San Francisco. How could you calculate the absolute shortest path? There are over 64 million intersections in the North American road system, so a simplified estimate gives around 10 to the 220 possible routes. Even if you could check 1 billion routes per second, testing all of them would still take over 10 to the 200 years. And this isn't just a problem for navigation software. Any independent system like a robot or a video game character that needs to navigate a maze or obstacle course faces this same problem. And yet, Google or Apple Maps will find you the route in only 4 seconds. So how is that possible? Well, we teamed up with the channel 2Swap, who creates incredible simulations and animations to show you step-by-step how these algorithms work. They trace their origins back to a shopping trip in Amsterdam in 1956. Edsger Dijkstra needed a problem. He was working on software for ARMAC, an early computer developed at the Mathematical Center in the Netherlands. And it was almost ready to debut, but at the time the general public considered computers to be practically useless. So useless, in fact, that Dijkstra ran into issues filing his marriage license.
Dutch marriage rights require you to state your profession, and I said that I was a programmer. But the municipal authorities of the town of Amsterdam didn't accept it on the ground that there was no such profession. And believe it or not, that under the heading profession, my marriage act shows the ridiculous entry theoretical physicist.
And so, Dijkstra was looking for a specific demo to prove just how powerful ARMAC was, even to the layperson.
The problem, of course, is that for a demonstration for non-computing people, you have to have a problem statement that non-mathematicians can understand. and they have to understand the answer.
And during that shopping trip, he thought of the perfect problem.
What's the shortest way to travel from Rotterdam to Groningen?
In other words, a shortest path algorithm. Here's a simplified graph of the Netherlands. The nodes represent the cities, and the edges connecting them are the roads. The simplest way to find the shortest path from Rotterdam to Groningen looks like this. Starting from Rotterdam, we're first going to explore all its neighbors, looking for Groningen. Since Groningen isn't one of these neighboring nodes, we'll mark Rotterdam as explored and keep searching. So now we'll branch out from these 4 nodes to explore all of their neighbors. And we keep branching out this way, exploring all neighboring nodes until we stumble upon Groningen. This algorithm is known as breadth first search. It will always find the shortest path because it checks all nodes 1 step away, and then 2 steps away, and so on. So if there were a path from Rotterdam to Groningen in 4 steps, we would have found it on the 4th iteration. But we didn't, so the shortest path must be 5 steps. But there's a problem with this approach. I mean, the algorithm considers all these roads to be the same length, which is obviously not true. So let's add weights to represent distances between these nodes. Now the shortest path is much harder to figure out. So Dijkstra needed a better method.
One morning, I was shopping in Amsterdam with my young fiancé, and tired, we sat down on the cafe terrace to drink a cup of coffee. And I was just thinking about whether I could do this.
His idea was this. First, he wanted to keep track of the shortest distance from the source to each node. This is also known as its cost. His goal? Well, if he could find the shortest path from the source to one node, then he could build up other shortest paths starting from this new node, and then the next, and on and on. Now, the cost of his idea was this. First, he wanted to keep track of the shortest distance from the source to each node. This is also known as its cost. His goal? Well, if he could find the shortest path from the source to one node, then he could build up other shortest paths starting from this new node, and then the next, and on and on. Now, the cost of the starting node was 0, but since he hadn't actually explored the rest of the graph yet, he set all the other nodes to a cost of infinity. Then, just like breadth first search, Dijkstra started from the source and explored each of its neighboring nodes. At every step he'd ask, is the current path to this node the shortest we've seen so far? For example, this edge only has a weight of 1, while the node's current cost is infinity. So this path is the shortest yet to that node. So Dijkstra updated its cost to 1. Likewise, these nodes were updated to 3, 2, and 4. After checking all of Rotterdam's neighboring nodes, Dijkstra marked it as explored. Then, since this node had the lowest cost out of all the unexplored nodes, Dijkstra explored it next. Like before, he checked each of its edges to reduce the neighbor's costs. Dijkstra could update this neighbor from infinity down to 6, a total path length of 5 plus 1. But he couldn't update this one. The current path has a cost of 5, but the node's cost was 3. That meant there was already a shorter path, this one directly from the source. So there was no need to update the cost. The next node to explore is this one with a cost of 2, which would update its neighbor to 5. Then this one with a cost of 3 would update its neighbors, and so on. Sometimes, Dijkstra had to update a node's cost a few times. For example, he first reached this node through this path with edge weights 4 and then 3 for a total cost of 7. But later, he found this path with cost 6, so he updated the node's cost again. The first time Dijkstra reached Groningen, it had a cost of 19, but it didn't have the lowest cost out of all the unexplored nodes. There was still this node with a cost of 16, which could be hiding a shorter path to our goal. So he continued exploring nodes in cost order and found this path with cost 18. Now, out of all the unexplored nodes, Groningen had the next lowest cost. So Dijkstra was confident that he'd found the shortest path. Here's why. If the lowest cost among the unexplored nodes is 18, then Dijkstra must have explored all the paths with cost 16, 14, 13, every path less than 18. And none of those paths reached Groningen. It's just like breadth first search, searching every step away from the source. By exploring from lowest to highest cost, Dijkstra's algorithm guaranteed the shortest path to any target.
It was a 20-minute invention. I designed it without pencil and paper. I learned later that one of the advantages of designing without pencil and paper is that you are almost forced to avoid all avoidable complexities.
During Armac's official inauguration in 1956, Dijkstra asked the audience members for 2 towns on a simplified map of the Netherlands. Armac then printed the shortest route town by town. It ran perfectly. The computer was such a success that the center immediately started the next generation. And as for his algorithm, well, it just sat in his papers for years. Algorithms weren't respectable enough for mathematics journals, and there weren't very many computing journals yet. But in 1959, he published his work in Numerische Mathematik, or Numerical Mathematics, a brand new German journal that needed some help getting established. And that was the beginning.
Eventually, that algorithm became, to my great amazement, one of the cornerstones of my fame. I found it in the early 60s in a German book on management science, Das Dijkstrasche Verfahren. Suddenly, there was a method named after me.
Dijkstra's algorithm is still regarded as one of the most elegant shortest path algorithms, but it isn't good enough for Google Maps.
Let's say I want to get from Newark Airport in New Jersey over to the Central Park Zoo. First, Dijkstra's algorithm checks all the 10-kilometer journeys, and then all the 20-kilometer journeys, and so on until it reaches all the 28-kilometer journeys, which includes the zoo. The search frontier covers over 65,000 nodes, and includes places that are way off, like Staten Island and large swaths of New Jersey. But even though it searched in illogical directions, the runtime was about 1/10 of a second, which is incredibly fast. And for anyone wanting to set up their own pathfinding tests, we were able to get a feel for these algorithms using some Python scripts and actual maps from OpenStreetMaps. Solving problems using code like this is as much about the journey as it is about the destination. You get to understand how Dijkstra works under the hood, but along the way, you also brush up on your coding skills. If that's something you want to try out, I strongly recommend today's sponsor, boot.dev. Instead of blinding you with code, their courses drill in the fundamentals by giving you actual problems to solve. Designing an RPG game, building a payment app, or yes, running Dijkstra's algorithm. Their courses start with overview videos and steadily feed in terminology to make sure that you actually understand it. They even cover pronunciation. You ever heard of squeal? Okay, it's SQL. Well, it's a programming language that's become a bottleneck for certain jobs. Take data science. 60% of US job listings last year required you to know SQL. That's almost 80% for Python. Boot.dev is geared up to teach you the languages and tools that you'll need for backend and DevOps roles, from Go and Docker to Linux and AWS. You can start from scratch or jump into more advanced topics. See, DevOps engineers in the US are still some of the highest paid tech roles because these skills are genuinely hard to learn. And that's the point. To get started, go to boot.dev and use our code Veritasium to get 25% off your entire first year on the annual plan.
I want to thank boot.dev for sponsoring this part of the video. Now, less than 100 milliseconds seems pretty fast. So what's the problem?
Well, things slow down a lot with bigger and bigger graphs, like the North America network. One way we can compare search algorithms is by their average query speed. First, we pick lots of random points. Then we run Dijkstra's algorithm on each pair of points and average all the runtimes. On the North America network, a well-tuned Dijkstra takes around 7 seconds per path. And for a lot of these searches, the algorithm has to explore most of those 64 million nodes. One note, most of the queries in this average are for very long journeys, since it's unlikely that 2 randomly picked points will be close together. Now, we've seen that Dijkstra runs much faster within one city, but this average is a good way to compare pathfinding algorithms. But still, I can wait 7 seconds. I mean, it took about 4 seconds on my phone. But the thing is, it's not just me. I'm waiting in a line behind Derek, Gregor, Casper, and all of you. There can be millions of people asking for directions all at once. And while Google has a lot of servers, there's a limit. If we want Google Maps to run in a couple of seconds, we actually need the algorithm to run in less than a millisecond, something 7,000 times faster than Dijkstra's. Well, one problem with Dijkstra's is it searches in the opposite direction of the target. So if we know the rough direction, is there a way that we can punish illogical routes? Let's go back to our problem getting from Newark to the Central Park Zoo.
We like to prioritize nodes that are closer to the zoo. So using longitudes and latitudes, we can easily calculate the straight line distance between any node and our target. We'll order the nodes by their cost plus this straight line distance. A great way to visualize this comes from the channel Polylog. We can represent each node's straight line distance to the target as its height, so the graph stretches into 3D space. The further a node is from the zoo, the higher it is. So the algorithm penalizes moves that climb up the graph. That way, nodes in the opposite direction aren't explored early on. So while Dijkstra's search frontier spreads out in all directions, this modified Dijkstra's, also called A*, immediately heads toward the zoo. It only checks around 7,000 nodes, which is almost a 10 times improvement over Dijkstra's. And by changing this penalty, also called a heuristic, we can tweak how aggressively A* targets the zoo. The steeper the slope, the less A* spreads out. It's a more human approach to finding the shortest path, since we're only exploring in the rough direction of the target. That's why A* is one of the most popular algorithms behind video game NPCs. For example, path, since we're only exploring in the rough direction of the target. That's why A* is one of the most popular algorithms behind video game NPCs. For example, many of the mobs in Minecraft use a version of A* with extra penalties for dangerous zones. It's also a popular maze-solving algorithm. At worst, A* checks as many nodes as Dijkstra, but on the right maze, it can cut down the search space by more than half.
But when I'm trying to get somewhere, I don't care about minimizing the distance. I just want to get there the fastest.
To optimize for time, we divide the straight line distance by the maximum speed allowed on the graph. This gives us the minimum travel time. But this heuristic is an extreme underestimate.
If you want to go for the shortest path in the sense that shortest geographic distance, you will gain some advantages using A* compared to base Dijkstra. If you go for travel time, that is, A*, from my experience, loses against a well-tuned Dijkstra. You explore fewer nodes, but not that many. But you now also have to evaluate quite a few heuristics that you would not need to evaluate when doing pure Dijkstra. And those contain like a nasty square root computation.
On our New York City graph, Dijkstra's algorithm explored around 9.5 times more nodes than A* to find the shortest path by distance. But if we switch that to the shortest travel time, the number of nodes A* explores triples, while Dijkstra only increases by 10%. And it only gets worse on larger graphs. So Google Maps needs something better that works well for travel time. What if we ran the search in both directions, from the source to the target and from the target to the source?
If 2 points are a distance r away, Dijkstra searches most of the nodes roughly within a circle of area pi r squared.
But with 2 searches, the frontiers will overlap around r/2 and cover an area of half pi r squared, half that of the single search. And depending on the graph, it can sometimes be better than half. A basic Dijkstra search from Carnegie Hall to Wall Street explored over 7,200 nodes. But a bidirectional Dijkstra explored a little over 2,600 nodes, close to a 3 times improvement.
But even a bidirectional search doesn't take advantage of the logic built into road networks.
They still do things that you wouldn't necessarily conceive as a good idea, right? Like they still look at the drive-through, at in and out, and see if there isn't perhaps a shorter path if you drive halfway into it, and then some clever way out of it, right? So maybe that is the intuition between why kind of Dijkstra and A* itself don't suffice. Both of them still kind of don't have a good sense of the hierarchy of the road network.
When I think about how to get from one place to another, I know that I'm probably going to meander around some local roads, then hop on a highway. And then when I'm close to my destination, I'm going to hop off the highway and meander around some more local roads. There's a hierarchy to road networks, but these algorithms can't take advantage of them. So they're as likely to search a twisty local road as an interstate highway, as long as they have the same weight. So how do we actually encode that human intuition into an algorithm?
If you look at kind of industry implementations in the 90s, for instance, like in these early in-car GPS systems, they had like a pre-computed road class that they annotated on the roads.
So here was the basic idea. Surveyors would go out and take notes about a road, like its speed limit, how wide it was, whether it was a highway. And then they would send that to the mapping companies who would manually categorize it into hierarchies. An example of a hierarchy might be express highway, local major road, or narrow road, like this.
Once it had the maps, GPS would run a bidirectional Dijkstra. But there was a catch. It first searched all the narrow roads within a candidate area. If it didn't find the target, it mapped a path to the next hierarchy, the major local roads, then searched all the major local roads within the new candidate area. If it still didn't find the target, it moved up again to the highway level. The two searches would overlap at some point and return the final path. This way, a little pre-processing could reduce the search area and take advantage of the road hierarchy.
One obvious downside here is that how do you correctly compute those levels of hierarchy, and how can you prove to yourself that they are correct in the sense that you are not missing any shortest paths?
For example, if the candidate area is too small, there's a chance the algorithm returns a highway path when a series of local roads really is better. A much larger candidate area might always find the shortest path, but at some point, that's not much better than Dijkstra.
If Google wanted to map the world, they need a better routing algorithm. Using a pre-processed hierarchy gives us way faster query runtimes, but there's a trade-off. Our brute force algorithm from earlier, where we just calculated all the paths to get the shortest one, is a perfect example. If we had a massive lookup table of all the shortest paths from any 2 points, then we would get insanely fast query runtimes. But building that list would take way too long. Here I have a graph. On the vertical axis is query runtime, and on the horizontal axis is pre-processing time. In the case of our massive lookup table, it would be right about here.
Even running Dijkstra from every one of those 64 million intersections, that's more than a decade of compute on a single core. And the entire table would be more than 8 petabytes of raw data. That's like storing all of Wikipedia, 16 times over. And even if we had the table, we'd have to rebuild entire portions whenever a road closes, a new bridge opens, and for every small traffic adjustment.
Now, in reality, it would probably not even fit on this chart. But for now, we're just going to put it here. On the other hand, Dijkstra's algorithm requires no pre-processing at all, but it takes a long time to run. So on our graph, it would fit about here. Google Maps needs something in between. Very fast query runtimes, but not too much pre-processing. In that case, we want to be in this region. Now, the idea is very similar to the manual hierarchies, but with 2 major changes. First, we'll automatically pre-process our graph to order nodes by how important they are. An exit connecting 2 highways, quite important. The intersection to a tiny cul-de-sac, well, not as much. No more categorizing roads by hand. We'll still use a bidirectional Dijkstra's that only searches up the hierarchy from both directions, but if we build it clever enough, we can get rid of candidate areas and still guarantee the shortest path. So phase 1 is building this hierarchy. How do we pick the most important nodes, though?
Let's take a look at these 2 small towns. We're gonna throw away everything in one town except for this house for right now. If someone in that house wants to get anywhere, they have to pass through this intersection at the end of the bridge. All of the shortest paths to and from their house include that node, so it's pretty important to them. But that node isn't as important to the rest of the town. After all, the only reason to cross the bridge is to get to that one house. But with more and more houses on the other side, the bridge node gets more and more important. Any trip from one side to the other needs to use it. It's the most important when the 2 towns are roughly the same size, when it splits the graph in half. That's when the maximum number of shortest paths include that bridge. There are other sets of nodes that split the graph in half, like this main street, but there's far more intersections along that street than just the one bridge node. So a small set of nodes, or a small cut of nodes, is important when it roughly splits the graph in half. Let's bring back the North America network. These blue nodes roughly split the graph in half. If you wanted to get from anywhere on the East Coast to anywhere on the West Coast, you'd have to go through one of these 102 nodes. It's just like the bridge connecting the 2 towns.
That's really small, but if you look at where does this thing go, that's essentially the Mississippi River. And bridges over the Mississippi are expensive to build.
These are the biggest bottlenecks. Out of all the 64 million plus nodes, these 102 get the highest rank, so the biggest numbers. Now let's find the next most important nodes.
Well, what can we do on both sides? Well, we can do the same thing. We again search for small cuts.
The next cut on the East Coast follows the Ohio River. most important nodes.
Well, what can we do on both sides? Well, we can do the same thing. We again search for small cuts.
The next cut on the East Coast follows the Ohio River, and then it loosely traces up the Appalachian Mountains before heading back south along the Potomac River. On the West Coast, the cut mostly follows the Rockies, and then the Colorado River. These two sets get the next highest ranks for their sides. And we can split these in half again and rank those nodes, and again, and on until we've ranked all 64 million nodes. This is called nested dissection. This pre-processing step has two goals. We want an algorithm that doesn't search a lot of nodes, so the runtime is really fast, but also will always return the shortest path. The hierarchy we build now needs to support both of these goals. Let's test this out on a smaller graph. We ignore the edge weights for the first step. These two nodes split the graph roughly in half, so we give them the highest rank. Looking at one side, this node splits the subset in half, so it has the highest rank of the three. We can rank the remaining two nodes in any order. Now, on the other side, these two nodes split this subset in half, so they have the next highest rank. And then again, we rank the final two nodes with the remaining numbers. But what about this ranking? We split the graph the same, but the rankings within the same cut are all swapped around. Or if we split the graph differently, we could get this ranking. It even splits the graph perfectly in half. Isn't that better? And these rankings are all valid. We'll see in a bit why we could use any one of them, but for now, we'll just take this one. The best way to visualize this ranking is to pull down or contract the nodes in order. 1 is the furthest down, 2 is next up, and so on. Now we can bring in a search algorithm. To speed up the runtime, we limit the search space by only moving up the hierarchy. And that's why it's so important to use a bidirectional Dijkstra. If the algorithm couldn't search in both directions, it would get stuck on a lot of pairs. So instead, the two searches meet in the middle at the top of the hierarchy. Now let's add the edge weights back. Okay, what's the shortest path from node 4 to node 8? Well, starting from node 4, we search up and reach node 9 with a cost of 10. From node 8, we also search up and get to node 9 with a cost of 5. So that must be the shortest path with a cost of 15. Done. Except there's a problem. That's not the shortest path. Using this path only costs 3. This search doesn't check paths that go through lower ranked nodes, but we can fix it with a little more pre-processing. Start from the lowest rank. Does this node connect to at least 2 higher nodes? On this graph, node 1 connects to 3 and 8. This is called a lower triangle. And while there's a chance this path is actually the shortest between node 3 and node 8, our search will never consider it. So we'll add a shortcut between nodes 3 and node 8 that's just the cost of this lower triangle. Now, this edge doesn't correspond to anything real on the road network, it's just a way to keep track of shortest paths. We move on to the next lowest node and run the same test. But there could be multiple lower triangles, or there might already be an edge between the 2 higher nodes. In those cases, the shortcut represents whichever path has the minimum cost. A path that only uses lower ranked nodes is like a path that only uses small local roads. We don't want the algorithm to return a highway route if a local road is shorter. Building shortcuts from the bottom up makes sure we don't miss these paths while also ignoring them if they aren't needed. This way, we both limit the search space and never miss the shortest path. But there's another benefit to shortcuts. We don't need to worry too much about getting a perfect ranking. We can roughly cut the graph in half and rank nodes in the same cut in any order. If the ranking overlooks the shortest path, well, we'll add it back later with a shortcut. That's why we were able to get 3 valid rankings using the same instructions earlier.
But while any ranking will still find the shortest path, a bad one will go really slow, or it'll quickly blow the graph up.
For example, with a series of nodes in a straight line, we don't need to add any shortcuts if we just contract the nodes from left to right. But when we search between the 2 ends, for example, with a series of nodes in a straight line, we don't need to add any shortcuts if we just contract the nodes from left to right. But when we search between the 2 ends, we have to explore every node and edge. That's no improvement over Dijkstra's. Here's another possible ranking with the necessary shortcuts. End to end, we only need to search 2 edges, but we need a lot of shortcuts, and in some sections we still have to check all the edges. Manageable, but not very efficient.
And so you want to have this trade-off between the number of shortcuts that you introduce and how much faster the query gets.
In practice, the nested dissection method gets a decent node ordering and doesn't take too long.
This entire algorithm is called a customizable contraction hierarchy. And Ben tested it out on the North American network to give us a sense of the runtimes. In Phase 1, we order the nodes and add shortcuts. This doesn't change unless the graph itself changes, like a new bridge or a road closure. It's by far the most expensive part of the process, but once it's done, it hardly ever changes.
I think it ended up at an hour 40 or something like that. You can spend more time, you get better results. So there's an argument to make that that's a good idea.
In Phase 2, we calculate the weights for all the shortcuts. Whenever there's traffic updates, we'll have to rerun this step, so it needs to be relatively quick.
I think 7-8 seconds without parallelization. Can get it down to about a second. And then that's where the memory starts hitting.
Finally, Phase 3 is the actual search. Remember, for a long path on the North American network, a well-tuned Dijkstra needs to explore most of the 64 million nodes and takes around 7 seconds per path. For this contraction hierarchy, the query runtime was around 200 microseconds.
Depending on how you configure stuff, you can get down to like 100 microseconds or so. But for practical purposes, below a millisecond is all you need.
That's 35,000 times faster than Dijkstra in just this experiment. And on average, it only needed to explore 1,450 nodes, cutting the search space by a factor of around 44,000. A Dijkstra search from San Francisco to Montreal would need to check all the nodes roughly in this area. On a customizable contraction hierarchy, it only needs to search these 1,236 nodes. Most of the nodes cluster around the source and target. Once it gets far enough up the hierarchy, it only needs to check the most important cuts, like the Mississippi. While we don't know exactly what Google Maps, Apple Maps, or any of these big routing applications actually use under the hood, they all could be built with contraction hierarchies. And customizable contraction hierarchies is just one variation, and there are even more routing algorithms that we haven't covered.
But if you think about it, its core search is still Dijkstra's, a 70-year-old algorithm.
4 decades after Dijkstra published his article, Danish computer scientist Miguel Torup said that all theoretical developments in single-source shortest paths have been based on Dijkstra's algorithm. And since 2000, many of the newest shortest path algorithms still use bits and pieces of Dijkstra's. From variations on contraction hierarchies, all the way to a recent theoretical breakthrough for an even faster shortest path algorithm. All of this based on a 20-minute invention. Part of Dijkstra's enduring success comes down to just how simple it is. As he said, simplicity is prerequisite for reliability. Dijkstra thought deeply about problems before ever touching a pen, because at the end of the day, it would be a programmer who was accountable for their work, not the machine.
Als je in de fysica iets niet begrijpt, je kunt je altijd verschuilen achter de ongepeilde diepte van de natuur. Je kunt altijd God de schuld geven. Je hebt het zelf niet zo ingewikkeld gemaakt. Maar als je programma niet werkt, dan heb je niemand waar je je achter kunt verschuilen. Je kunt je niet verschuilen achter onwillige natuur. Nee, een 0 is een 0 en een 1 is een 1. En als het niet werkt, dan heeft het gewoon fout gedaan.
So with those 2 ideals, he hoped to have one lasting legacy. He said, if 10 years from now, when you're doing something quick and dirty, you suddenly visualize that I'm here looking over your shoulders and say to yourself, Dijkstra would not have liked this. Well, that'd be enough immortality for me. So even if you can only control your little corner of the world, you can still make it as elegant and thoughtful as possible for you and all the people who come after. Before we go, I just wanted to say thanks again to boot.dev for sponsoring this video. If you guys want to check them out, you can check the link in our description or scan this QR code right here. And make sure to use at checkout code Veritasium for 25% off. So thanks to boot.dev, and I also want to thank you for watching.
You have arrived at your destination.
There is a pre
There is a prequel to the Da Vinci Code. It's called Angels and Demons. There is a prequel to the Da Vinci Code. It's called Angels and Demons. And in it, terrorists steal 1/8 of a gram of antimatter from CERN to try to blow up the Vatican. Because the thing is, when antimatter and matter meet, they annihilate, turning nearly when antimatter and matter meet, they annihilate, turning nearly 100% of their combined mass into pure energy. This is via E equals mc squared. It is the most violent process physics allows.
Let's go!
Oh my god. Now, that was just a novel, but CERN actually is making antimatter. And we got to visit it. This is CERN's antimatter factory. There's antiprotons going beneath our feet.
They are under our feet at this time.
Here, protons are accelerated up to 99.93% the speed of light and smashed into an iridium target to produce 20 million antiprotons every minute. This is so much bigger than I was thinking. This is crazy. Antimatter is the most expensive substance in the universe. $1 billion per gram.
No way, go up. We are missing zeros here.
And CERN makes it to do something that seems impossible. So you're making anti-atoms? Yes. CERN made the first anti-hydrogen atoms back in 1995. But they quickly ran into a problem, because those anti-atoms only survived for 40 billionths of a second before annihilating, which is way too short to do anything useful with it. If only they could figure out how to store antimatter, then they could study it and try to find ways in which it might differ from normal matter. They knew that any unexpected difference could reveal entirely new physics. So how do you store antimatter in a world full of matter? Well, that's one of the problems CERN has been obsessing over for the last 30+ years. It has allowed them to do some of the most precise tests of antimatter to date, and they even managed to trap a world full of matter. Well, that's one of the problems CERN has been obsessing over for the last 30+ years. It has allowed them to do some of the most precise tests of antimatter to date, and they even managed to trap antimatter in a box, load it onto a truck, and ship it. And they are doing all of this to try and solve one of the biggest unsolved mysteries in all of physics. To understand it, we must go back to a discovery made around 100 years ago. Previously on Veritasium, we learned how a strange physicist, Paul Dirac, came up with an equation to unite special relativity with quantum mechanics. It worked surprisingly well, but Dirac was stumped by his own equation, because the solution for an electron at rest was kind of strange. There were two possible energies, E equals mc squared and E equals minus mc squared. But how could an electron have negative energy? Well, instead of throwing away his negative energy solution, Dirac ended up proposing something radical. This negative energy solution corresponded to an entirely new particle, unknown to physics at the time. It would have the same mass as an electron, but carry opposite charge. It would be an anti-electron, or positron. Miraculously, a year later, the first positron was observed by accident in nature. Over the following decades, physicists built on Dirac's equation to form an entirely new framework of quantum mechanics. Quantum field theory. This didn't just explain why there are antiparticles, but it also answered a more fundamental question, which is, why is every electron in the universe exactly the same? The answer began to take shape when people figured out that fundamental particles aren't just particles or waves, but rather excitations of a quantum field. So you'd have an electron field that permeates all of space, and this field can get excited, but only in identical discrete units, each with the same mass, spin, and charge. And that's why every electron is the same. They're all excitations of the same field. Now, you could have several excitations, that would be several electrons, and they can move around too. The only requirement is that they can never overlap exactly. Of course, there is nothing special about this kind of excitation. You could just as well have a mirror opposite. In fact, the equations that describe this field require such excitations to exist. They have the same mass and spin, but with opposite charge. This is the idea of an anti-electron, or positron. It's exactly what that minus sign in the reqs equation was revealing. And just like an electron, positrons can move around too. Only positrons can overlap with electrons. But watch what happens when they do. It was revealing. And just like an electron, positrons can move around too. Only positrons can overlap with electrons. But watch what happens when they do. Now, I'm simplifying a little here, but because they're each other's mirror images, the opposite charges cancel each other out. The excitations disappear, and the field returns back to its ground state. But that would predict that the particles just disappear. So how is that possible? Where did the mass go? Well, the only way this could work is if that mass got converted into something else. Energy, according to E equals mc squared. The energy got transferred into a different quantum field, the photon field. And that is what we mean by annihilation. Now, people realize that most, and that is transferred into a different quantum field, the photon field. And that is what we mean by annihilation. Now, people realize that most fundamental particles could be described using the same approach, where each could be seen as an excitation of their very own quantum field. Now, this meant two things. The first is that most particles must have an antiparticle twin, because they're just mirror excitations in the same field. There are some exceptions though, like the photon and Higgs boson, which are their own antiparticle. And the second and more important implication is that each antiparticle must be exactly equal to a normal particle, just with the opposite charge. But then, around the mid-1960s, people realized that there was a big issue with this explanation. And it all stemmed from how it fit in with the newly accepted Big Bang theory. In the very first moments after the Big Bang, the universe was extremely hot and dense, and photons had so much energy that the reverse process of annihilation happened. So two photons could come together and spontaneously convert their energy into the mass and kinetic energy of a particle-antiparticle pair. And so the universe was filled with these pairs continuously popping into and out of existence. But as the universe continued to expand, it cooled, and those photons lost energy. Until around 3 seconds after the Big Bang, they had lost so much energy that pair production stopped. And this is what troubled physicists in the 1960s, because they believed that in those initial stages, an equal amount of matter and antimatter should have been created. But if an equal amount of matter and antimatter were created, then every particle should have found its antiparticle twin and annihilated. Meaning there should be no stuff around us, no matter and no antimatter, just photons, only radiation. So this became known as the Big Bang radiation catastrophe. Because clearly, when we look around us, we see a lot more than just energy. The universe is filled with matter. But how can that be? Why is there now more matter than antimatter in the universe? Where did that asymmetry come from? Well, that is one of the biggest unsolved mysteries in all of physics. Initially, some people tried to brush this away, and they argued that perhaps there is no asymmetry at all.
Maybe we happen to be in a pocket that, because of blind random chance, some reasonable statistical fluctuations, we're mostly surrounded by matter, and there'd be some region that would again be like a Marvel movie, like some mirror universe that would be most slightly, imbalanced in the other direction.
Paul Dirac seemed to have favored this approach. He argued that there might be entire anti-stars, and he ended his 1933 Nobel lecture by saying, "There may be half the stars of each kind. The two kinds of stars would both show exactly the same spectra, and there would be no way of distinguishing them by present astronomical methods." Physicist Edward Harrison took this one step further, saying there should even be entire anti-galaxies.
And then people realize, well, if that's the case, there'd be regions where these boundaries where the two regions would meet, and that should be lighting up the sky. Should be tons of matter-antimatter annihilations. Should be tons of very high energy light.
So people surveyed the sky looking for these hotspots, but they didn't find any. And so this possibility was ruled out. There really is more matter than antimatter in our universe. There really is an asymmetry. So the next obvious question is, Well, how large is that asymmetry? If we go back to around 10 seconds after the Big Bang, we can figure it out. By this time, pair production had long stopped, a full 7 seconds ago. And by now, just about every antiparticle had annihilated with its particle counterpart and turned into photons. Now, the universe was filled with just some leftover particles, like electrons and protons whizzing around at incredible speeds, and those remnant photons. But because these electrons and protons were traveling so fast, they couldn't come together to form atoms. So you had this plasma of charged particles. And that meant that when photons were going around, they scattered off those charged particles. So they couldn't travel very far without interacting with matter. That all changed around 380,000 years after the Big Bang. By now, the electrons and protons had slowed down enough to form neutral atoms. And photons could only be absorbed by electrons in atoms if they had exactly the right energy to move the electron up an energy level. In practice, this meant that photons could now basically travel through space unimpeded. Those atoms then went on to form all the stars and galaxies, and those photons stuck around too. They've gone on to make up the low-level radiation that permeates the entire observable universe, the cosmic microwave background, or CMB. And when we estimate the total number of photons in that CMB, we find that there are about 10 to the 89. And because almost all of those photons were originally created during those very first seconds after the Big Bang, that original annihilation, we can infer that there must originally have been around 10 to the 89 particles and antiparticles. Now, we can also estimate how many ordinary matter particles, like protons and neutrons, there are in the observable universe today, the ones that survived that annihilation. And what we find is that there are about 10 to the 80. So that means that for every billion antimatter particles and billion matter particles there were in the early universe, when they annihilated, they did so almost perfectly. But there was one out of a billion matter particles that somehow survived. And everything we see around us today is a descendant of those lucky 1 in a billion particles. Every person, animal, jungle, and ocean, every asteroid colliding or galaxy spiraling, every single dot of light in the night sky is made up of one of those lucky 1 in a billion particles. And that brings us to the craziest part, because it tells us that there must be a difference between matter and antimatter, and how they evolve according to the laws of physics. But it's not just any difference. No, it would make sense if they behaved completely different. I mean, you would just have different laws of physics governing each type of particle. Or it would make sense if they were governed by the exact same laws. But in that case, there would be no difference. It would be completely symmetric. What's really weird here is that the laws are almost exactly the same, but with a tiny difference. And that doesn't make any sense. For the past 70 years, physicists have tried to explain where this asymmetry comes from. But so far, all attempts have failed. And part of the reason this has been so difficult is because our laws of physics are full of symmetry. In the mid-1950s, there were 3 symmetries all particles were believed to obey: charge, parity, and time reversal symmetry. Charge symmetry is super simple. It just means that if you swap all positive charges with negative ones, and vice versa, then the interactions don't change. In other words, there is nothing special about a positive or negative charge, just that one is exactly equal and opposite to the other. To understand parity symmetry, consider this mirror, which creates a sort of parallel universe, where everything is the same but reflected. So my left hand becomes my right hand and vice versa. Now take this molecule here, which is L-alanine, an important amino acid we need to make proteins. Now that L is in its name because the amine group, this NH2 part over here, is on the left. But in the mirror you see its sister molecule, D-alanine, that NH2 part is now on the right. And if you try to make alanine in a lab, you'll find that you'll get 50% L-alanine and 50% D-alanine. In other words, there is no experiment you could do that determines whether you're in our universe or in the mirror universe. And the same is true for many left and right-handed molecules. If you just try to make them normally in a lab, you'll get 50% of each. So our universe doesn't favor left or right-handedness. Lastly, time reversal symmetry means that the laws of physics work the same whether time is running forwards or backwards. Now, out of all of these, time reversal symmetry might feel strange, because there are many things that clearly don't work backwards in time. You can't uncook an egg, unshatter a wine glass, or turn a plant back into a seed. But all of these follow from the second law of thermodynamics, which describes how many interacting particles evolve from less likely states, typically more ordered, to more likely states, typically a mess. But this is a statistical law, it's not a fundamental law of physics. If you zoom in to the level of individual particles, then every interaction is But this is a statistical law, it's not a fundamental law of physics. If you zoom in to the level of individual particles, then every interaction is perfectly reversible. You can tell whether these collisions happen forwards or backwards in time. Now, the combination of all of these symmetries combined is called CPT symmetry. And CPT symmetry, it turns out, is kind of a big deal. What happens if CPT gets broken?
Well, literally, cats and dogs start living together. Time flows backwards. All kinds of things start breaking in our description of nature. Now, one of the reasons why CPT and the standard model go so well together is because it really is built into the very structure of special relativity.
Special relativity is built on one core principle, which is that the laws of physics are the same for all inertial observers, and this includes any measurement they make. Relativity is built on one core principle, which is that the laws of physics are the same for all inertial observers, and this includes any measurement they make of the speed of light. In the 1950s, Julian Schwinger, Gerhard Luders, and Wolfgang Pauli proved that if our universe obeys this principle, which we strongly believe it does, then it must be CPT symmetric. But the reverse is also true. If you break CPT symmetry, then this core principle also breaks. And that's where things get tricky, because after Julian Schwinger, Gerhard Luders, and Wolfgang Pauli proved that if our universe obeys this principle, which we strongly believe it does, then it must be CPT symmetric. But the reverse is also true. If you break CPT symmetry, then this core principle also breaks. And that's where things get tricky, because after Dirac united special relativity with quantum mechanics, all following quantum theories also incorporated special relativity. And so our best theories of reality, quantum field theory and the standard model, are built on that exact same principle. So now we have a paradox, because on the one hand, we need asymmetry to explain why we're here. But on the other hand, if CPT symmetry breaks, it tears down our best theories with it. So physicists started off on a hunt for a special kind of asymmetry. An asymmetry that could explain that 1 in a billion discrepancy while also maintaining the larger CPT symmetry. The first clue that such asymmetries might exist came in the mid-1950s. Up until then, every interaction that had been studied conserved the individual symmetries of C, P, and T, and so maintaining the larger CPT symmetry. It tears down our best theories with it. So physicists started off on a hunt for a special kind of asymmetry. An asymmetry that could explain that 1 in a billion discrepancy while also maintaining the larger CPT symmetry. The first clue that such asymmetries might exist came in the mid-1950s. Up until then, every interaction that had been studied conserved the individual symmetries of C, P, and T, and so conserved CPT as a whole. But in 1956, theoretical physicists Soong-Dao Lee and Chen-Nin Yang realized that no one had checked whether parity is conserved in the weak nuclear force. So they set out to test whether the and also maintaining the larger CPT symmetry. The first clue that such asymmetries might exist came in the mid-1950s. Up until then, every interaction that had been studied conserved the individual symmetries of C, P, and T, and so conserved CPT as a whole. But in 1956, theoretical physicists Soong-Dao Lee and Chen-Nin Yang realized that no one had checked whether parity is conserved in the weak nuclear force. So they set out to test whether the universe favored left or right-handedness. And to do it, they enlisted the help of one of Lee's colleagues, one of the world's best experimentalists, Chen Shung Wu, also known as Madame Wu.
Once the idea of the experiment was pitched to her, then she just went all in. She canceled trips. She worked straight over holiday breaks. It was really a all hands on deck operation over a very frenzied few months.
When Pauli learned of the experiment, he said, "I do not believe that the Lord is a weak left-hander, and I am ready to bet a very high sum that the experiments will give symmetric results."
Now, all that was left to do was run the experiment. It worked something like this.
She started with cobalt-60, an isotope of cobalt where the nucleus has an intrinsic angular momentum, or spin. When she applied a strong magnetic field, she forced all the spins to point in the same direction. But cobalt-60 is also radioactive, so when she applied a strong magnetic field, she forced all the spins to point in the same direction. But cobalt-60 is also radioactive, so every once in a while, a neutron inside one of its nuclei decays into a proton, releasing an electron and antineutrino, and leaving a nickel-60 atom behind. Now, the electrons emitted could travel in two directions. They could either go in the same direction as the nuclear spin, or they could go in the opposite way. But if spin is clockwise in our universe, then it is also clockwise when reflected in the mirror, which means it points in the same direction in both universes. So the only way the experiment could be the same in our universe and the mirror universe is if the electrons were emitted in equal amounts in each direction. It should be 50% on each side. But what Wu actually found was that around 60% of the electrons moved in the opposite direction to the nuclear spin, which would mean that 60% moved in the same direction as the nuclear spin in the mirror universe.
But that meant that there is an experiment you could do to tell whether you're in our universe or the mirror universe. So it proved that parity is not conserved. This shocked the physics community.
Pauli, upon being informed of the results, exclaimed, "That's total nonsense."
Very smart people, Nobel laureate, said, "That can't be right. Do it again. I don't believe it." And in a sense, you can see where they're coming from. There had been no hint as yet that kind of the universe would care whether I'm looking at myself, in a mirror or not.
So others repeated the experiment, and by 1957, there was no further room for doubt. God really was a weak left-hander. That same year, Lee and Young won the Nobel Prize in Physics for the discovery of parity violation. But Wu's name was left off. Lee and Young acknowledged her during their speech and tried to get her nominated for a prize another year. But the Nobel Committee never honored her. In a way, she was robbed of the Nobel Prize. 1988 winner Jack Steinberger called this the biggest mistake in the Nobel Committee's history. But her work had done something important. It had cast doubt on the long-held belief that charge, parity, and time reversal were fundamental symmetries of our universe.
This made many physicists uncomfortable, so they came up with a workaround. Maybe it's okay if parity symmetry was broken, because that's not a fundamental symmetry of nature, it's just part of a larger symmetry, charge parity. The idea was that if you reflected everything in a mirror and swapped all the particles for their antiparticles, then the symmetry would be restored and all would be good again.
But then, 7 years later, two physicists found that some particles also violated the combined charge parity symmetry.
Now physicists were getting really nervous. Two symmetries that they believed were fundamental parts of our universe were broken. So the next big question on everyone's mind was, is CPT symmetry also going to fail and take down the standard model with it? Then, in 1973, something seemingly miraculous happened. Makoto Kobayashi and Toshihide Masukawa found a way to explain all the observed P and CP violation while maintaining CPT symmetry. And it all fit directly within the standard model. The only issue is that when it comes to the matter-antimatter asymmetry, it can only account for an asymmetry of 10 to the minus 18. Which is a billion times less than we need to explain the observed matter-antimatter asymmetry.
So the ingredients are there, which is cool, because I didn't think even the ingredients were there. But they're not there in a large enough strength. You don't have a strong enough rate of CP violation if you just stick with strictly the standard model.
And so are people now getting nervous about CPT?
Not nervous, I'd say excited.
And that's because this means there is likely new physics beyond the standard model. But to find out what that might be, we must study antimatter up close, to see if there are any ways in which it might be different from normal matter, ways that could explain that asymmetry. So you know where we're going.
Oh, look, there it is. CERN, baby. Woo! CERN is best known for the Large Hadron Collider, a 27-kilometer underground ring where protons are accelerated up to 99.999999% the speed of light. Beams traveling in opposite directions are smashed together, releasing huge amounts of energy. It's the closest we get to the high energy conditions of the early universe. But at the southern edge of the LHC, there is a smaller proton accelerator. Called the proton synchrotron. Protons in this ring are only accelerated to 99.93% the speed of light. And some of that proton beam is fed out of the ring and ends up here.
This is CERN's antimatter factory. And in here, we make antiprotons.
Yes.
How many?
Usually it's around 40 million every couple of minutes. We are now going to enter the facility by actually a technical building, which is not very interesting to watch.
I find this all interesting to watch.
To make sure we're safe, we always had to carry around these devices.
So you've got two, what are they called?
Dosimeters.
Dosimeters.
Yes.
Yeah, just to be safe.
These are standard devices to measure the amount of dose of radiation that you get.
Yeah.
This is a supervised radiation environment, which means it's an environment in which we keep an eye onto the amount of radiation we get as radiation workers.
Where are we going now?
So now we are going to enter into the main building.
There's antimatter behind this.
Yeah.
Behind this door.
Yes, under our feet.
Oh wow.
Yeah, we see. You see. Please,
wow.
guys,
This
and
is
welcome.
huge. What?
This is a huge place.
This is so much bigger than I was thinking. This is crazy. Well, I feel like I'm a kid in a candy store looking at this.
This place is pretty fun, huh? The first time you see it.
Yeah, it's so impressive.
Here you see pretty much the scheme of how this facility is working. You get protons coming from one of the CERN accelerators, the PS, which smash onto a target.
The protons are accelerated up to around 99.93% the speed of light and have energies up to 26 giga-electron-volts. They're aimed at a remarkably small target, an iridium rod, 3 millimeters in diameter and 55 millimeters across, which itself is embedded in a graphite and then in a titanium alloy structure. Iridium was chosen because it's the second densest element on Earth. And that means that there are a lot of nuclei packed in a small space, which increases the odds that the protons will hit something. But when one of these protons hits an iridium nucleus, it doesn't bounce off like you'd expect in most collisions. It is going so fast and has so much energy that it penetrates the nucleus, where it collides directly with one of the neutrons or protons. And to understand what happens next, we need to look at what's going on inside the proton. Because a proton is not a fundamental particle. Instead, it is made up of 3 fundamental particles known as quarks, specifically 2 up and 1 down quark. Those quarks whiz around close to the speed of light. So to keep all those quarks contained, traveling at such incredible speeds and in such a small space requires a very strong force, which is why it's called the strong force. And it's mediated by particles known as gluons. You can think of this force as acting like a rubber band.
But you can bring this past its breaking point. If you keep putting in energy, then you can put in so much energy that another quark-antiquark pair will be created. This bond breaking into pair creation can happen several times in a row and results in this sort of shower of quark-antiquark pairs.
And a similar thing happens when a proton collides with a neutron or proton inside an iridium nucleus. Now, most of those pairs stay just like that, pairs, and they travel off. But occasionally, you will get 2 anti-up and 1 anti-down quark to come close enough, and they form a new particle made of 3 antiquarks. They form an anti-proton, and their counterparts will go on to form a proton.
Now, all of this entire process, from initial collision to the shower of particles and the formation of the antiproton, happened in the span of 10 to the minus 23 seconds. That is 100 billionth trillionth of a second. It is absolutely insane. And every time you hit the target, you get trillions of these collisions. And out the other side comes a chaotic spray of protons, antiprotons, and a bunch of other particles, all traveling at around 96% the speed of light. Magnets then filter out the antiprotons from the other particles and they're sent on to the next stage.
And then we collect these antiprotons, bring them into the ring, the antiproton decelerator ring, which is the one we are staring on top of, and then they circulate in the AD for a while they get cooled down. So the idea here is really that we get these antiprotons every 2 minutes, more or less. It's about 30 million of them.
How expensive is it, antimatter?
Look, guys, what is value? It's a bit difficult to evaluate it, right? For sure, it's probably the most expensive state of matter we can build on Earth today.
How about I name some numbers and you tell me if it's cheap or too expensive?
Shoot.
$1 billion per gram.
No way.
It's too cheap?
Orders of magnitude too cheap. But
Okay.
many orders of magnitude too cheap.
That's what I was thinking. $100 billion per gram.
No way, go up. I think probably you miss other 3 zeros.
3 zeros?
I think so, per gram, yes.
That's
at least.
crazy.
If you're wondering what you would do with all that money, you should check out today's video sponsor, SoFi. SoFi is an all-in-one finance app that lets you bank, borrow, and invest. And with their premium membership, SoFi Plus, you get benefits such as investment matches, unlimited access to financial planners, and a competitive APY on savings to earn interest on your money. All so you can let your money work for you. By adding up all of these benefits, you could unlock $1,000 or more in annual value with qualifying activities. Of course, it depends on how you use the app, so check if it's right for you. And you can get started by subscribing to SoFi Plus for just $10 per month. Right now, they're also running a promotion for US residents. So if you join SoFi Plus between now and April 15th, you'll automatically be entered into their giveaway for a chance to win $75,000, as well as other cash prizes and free memberships. So to check out SoFi Plus, head to sofi.com/Veritasium or click the link in the description. I'd like to thank SoFi for sponsoring this video, and now back to antimatter.
There's antiprotons going beneath our feet.
They are under our feet at this time, yes,
Okay.
indeed.
And that's not dangerous.
No, it's not dangerous.
Okay.
There is no risk whatsoever.
Strong electric fields in the decelerator slow down the antiprotons from 96% to 10% the speed of light. But that's still about 100 million kilometers per hour. To do experiments with them, they need to be slowed down more.
Initially, this was done in a kind of crazy way. The antiproton beam was fired at a thin plastic foil, which annihilated 99.9% of all the antiprotons. But around 0.1% of those antiprotons survived, and they came out slow enough to do experiments with them. Of course, this was very inefficient, and so in 2015 and 2016, a secondary ring called ELENA was installed. ELENA slows the antiprotons to 1.5% the speed of light. A nice, slow 16.2 million kilometers per hour.
This is running.
You are watching a live antiproton machine.
Are the antiprotons going around in these circles?
Exactly. The blue devices are magnets, dipole magnets, which by Lorentz force make the particles turn. Then you have the orange ones, which are quadruple magnets, which manage the focusing of this beam. They're like lenses for particles.
It's a pretty thin pipe almost that they go
Yeah,
through.
I mean, you don't need much there, right? Because as long as you don't bend the particles, they just want to go straight. You need to keep good vacuum in there, very good vacuum, in fact.
Yeah.
Otherwise, they would annihilate.
And how often do you have annihilations in this loop?
In here?
Yeah, because you can't have perfect vacuum.
Well, no, you have a bit of losses, but you know, the entire process of catching, I mean, from the moment of catching to the moment of extraction to the experiments, I think these days we are about 86% efficiency. They have made it very efficient.
After the antiprotons have been slowed down in ELENA, they're sent onto 5 different experiments. each of which is designed to study different properties of antimatter, to try and find ways in which antimatter behaves differently from normal matter. One of the first experiments that was done, which happened before the antimatter factory was built, was testing whether the mass of a proton and antiproton are the same. But to do that, it brings us back to our original problem. How do you store antimatter? The way they solved this problem is pretty clever. They started with a tube which was pumped down to a vacuum. A superconducting magnet sits around this tube, and it creates a magnetic field that confines charged particles to the center. At the same time, electrodes generate electric fields that function as end caps, preventing the particles from escaping out the ends. The whole tube is then cooled down to around 4 Kelvin, or minus 269 degrees Celsius. This causes almost all the remaining particles to condense and freeze, resulting in a vacuum pressure comparable to outer space. So now they could fill this tube with something like antiprotons. And once inside, those antiprotons have nothing to annihilate with and nowhere to go. They are trapped. They had just built a real-life antimatter trap. The technical term for this is a Penning trap, after Franz Penning, whose work inspired the first one. Fittingly, the team that did this at CERN was called TRAP. With the antiprotons trapped, they measured the charge to mass ratio of the antiproton and compared it to that of the proton. And they found it was equal to 1 part in 10 billion. Now, the Penning traps made studying of the antiproton and compared it to that of the proton. And they found it was equal to 1 part in 10 billion. Now, the Penning traps made studying antimatter much easier, and so it became a key tool that the other experiments at the factory adopted. In 2017, the BASE experiment used it to measure the antiproton's magnetic moment, and they found that, within their level of accuracy, it was equal and opposite to that of the proton. So, thus far, everything was behaving just as predicted. But there is one force that they hadn't directly probed yet: gravity. Gravity, could that be part of the solution?
It very likely will be ultimately. Part of why is because gravity does not obey the rules of special relativity, which means it doesn't have to obey the CPT theorem like the CERN model does. And so in principle, that's an area within which one could more naturally expect larger values of violations of C and CP and so on, or even a CPT altogether.
In fact, back in the 1950s, a few physicists entertained the idea of anti-gravity, that antimatter would be gravitationally repulsive. So while matter falls down in the Earth's gravitational field, antimatter would rise up.
You had a basketball made of antimatter, that would be easy to test, but getting a basketball of antimatter without it blowing up on you is pretty hard. So it's not an easy thing to do gravity experiments on particles.
You can't just drop an antiproton and see if it falls, because antiprotons are negatively charged, and the electric force is much stronger than gravity. So even are negatively charged, and the electric force is much stronger than gravity. So even small stray electric fields would influence them way more than gravity would. So what you need is stray something neutral. What you need is an anti-atom.
So you're making anti-atoms.
Yes.
How do you make the anti-atom?
So what we do is we use antiprotons and positrons. Basically, we merge them. They become anti-hydrogen.
Now, there are several ways to make anti-hydrogen, and different experiments do it in different ways. But for G-bar, it all starts here, in this bunker.
In this bunker, we have a small accelerator. So we make ourselves our own positrons, and then we capture them in a trap here.
They accelerate a beam of electrons up to 99.9% the speed of light, and then fire those at a tungsten target. Now, while tungsten itself is electrically neutral, at the height of electrons up to 99.9% the speed of light, and then fire those at a tungsten target. Now, while tungsten itself is electrically neutral, at the high speed those electrons enter the tungsten, they get close enough to the nuclei that the electron cloud can no longer screen the intense positive charge within. Thus, these nuclei create strong electric fields, and those fields then yank the electrons around, causing them to rapidly decelerate, as if they've just slammed on the brakes. But the thing is, when these electrons break, they lose energy by emitting photons. The Germans have a great word for this. It's called Bremsstrahlung, or braking radiation. This braking radiation produces a wide range of photons, ranging from low energy X-rays all the way up to nearly 9 mega electron volt gamma rays. Now, out of all of these photons, it's the gamma rays above roughly 1 mega electron volt that are important. Because when one of these gamma rays passes close to a tungsten nucleus, there's a chance that it transfers its momentum to that nucleus and converts all its energy into the mass and kinetic energy of an electron-positron pair.
But unfortunately, this isn't a clean process that just makes electron-positron pairs.
It produces positrons, but it also produces a lot of photons, gamma rays, neutrons, and these are deadly.
And that particle mass creates two problems. The first is that deadly radiation.
It's supposed to be one of the highest, strongest source of radiation at CERN.
This is one of the highest.
Yes. If you enter while it is working, you die in 10 seconds.
You die in 10 seconds?
You cannot escape.
It's terrifying.
You melt from inside.
You melt from inside. You're saying that way too casually.
And the second problem is that what comes out of the tungsten isn't a nice uniform beam of positrons. Instead, you get a shower of electrons, neutrons, positrons, and photons all mixed together, all traveling at different angles and different speeds. And photons. Instead, you get a shower of electrons, neutrons, positrons, and photons all mixed together, all traveling at different angles and different speeds. The first problem is solved by encasing the entire setup with massive 1.2 meter thick, 67% concrete and 33% iron blocks.
And this is enough to shield us?
Yes.
Because it's photons?
Yes. This is 1,400 tons.
Okay, I feel a bit better now. Is it running now?
No, but even if it runs, we can see just outside and it's okay.
Okay, so we're safe. You wear your
badge, dosimeter.
Okay, so you would know.
Yeah.
But I guess 10 seconds, not.
Too late.
Too late.
Solving the second problem is a little more involved. And it's honestly one of the coolest combinations of physics and engineering I've ever come across. So strap in.
When the positrons leave the tungsten target, some are traveling at a few percent the speed of light, while others are traveling at more than 90% the speed of light. Now, this massive spread makes it very hard to work with, so we need to slow them down to around 0.34% the speed of light, or around 3.7 million kilometers per hour.
The way they do this is kind of crazy, because they shoot the positrons, remember, those are antiparticles, at a mesh of ultra-fine 20 micrometer diameter tungsten wires, which of course are made of normal matter. When a fast positron enters the tungsten wire, it immediately loses energy due to scattering off the tungsten atoms. And this happens so fast that within around 10 picoseconds, that is 10 trillionths of a second, the positron has slowed down to match the thermal energy of the tungsten. But now the positron is still trapped inside the wire. So from here on, through a random walk of collisions and scattering, it needs to find its way out. And if it bumps into an electron or gets stuck in a defect, it never makes it out. So you might expect almost none of these positrons to make it out, and for almost all of them to find an electron and annihilate. And you'd be right. The efficiency of this process is terrible. For every 1,000 fast positrons entering the mesh, only about one comes out as a usable slow positron. Another problem is that these positrons don't come out as a nice organized beam. Instead, they are emitted at all kinds of angles, so we need to find a way to focus them. This is done by letting the shower of particles go through a solenoid, which is a long coiled wire with a current running through. That current creates a magnetic field inside the coil that acts as a magnetic lens and focuses the positrons. This lets us capture many of the positrons emitted at wide angles that would otherwise be lost. But right now, we still have a mix of positrons, electrons, neutrons, and photons.
So the next step is to separate these. To do this, we use another magnetic field. This curves the electrons one way into a beam dump. The photons and neutrons, because they have no electric charge, are unaffected, so they go straight through and are absorbed by shielding. And the positrons, because of their positive charge, curve the opposite way to electrons, and they go on to the next stage. Now we're left with a beam of just positrons. The only issue is that because of the terrible efficiency from slowing down those positrons, each single shot only generates around 1,000 usable slow positrons. But we need millions or even billions of slow positrons for the next stage. So the solution is to accumulate the positrons in a particle trap, where over several minutes it builds up a positron cloud of around 100 million or more positrons, which is enough for the next stage.
Oh, I said you merge positrons and antiprotons, but we do even more complicated. First, we make positronium. Positronium is
Positronium?
Yes.
Positronium is an electron and a positron orbiting each other like a binary star system. It's an exotic form of matter, and it only lasts about 1/10 to 142 nanoseconds before the two come together and annihilate. The way they make this is by using strong magnetic fields to compress the cloud of positrons and fire it at porous silicon dioxide films. When these positrons enter these films, they rip away electrons from their atoms, and some of those electrons then bind with positrons to form positronium. And then a part of that positronium diffuses out of the films into the vacuum of the next stage, the interaction chamber, where it's time for the final step.
So this is what we prepare this here.
That's the positronium.
Yes.
That's crazy.
We send antiprotons to the positronium where it makes antihydrogen.
Now, since positronium only survives for about 142 nanoseconds, this needs to be timed perfectly.
So if you want to see where we catch the antiprotons.
Yes, I would love to see where you catch the antiprotons. I was not expecting to get this close. It's right here?
Yes.
That's awesome. Yeah, so we get the antiprotons here.
Yes.
And then what happens?
So it goes there inside this box.
Yeah.
Inside the box, it will meet the positronium.
Oh, there meets the positronium. Kind of scared, honestly. It sounds like there's music in here.
As the positronium enters the interaction chamber, the antiproton beam needs to be fired through at that exact moment. When done correctly, around 3 million antiprotons or so pass through the positronium. If all goes well, around 1 to a few of those antiprotons steal a positron to create an atom of antihydrogen.
Okay, so we've got
well, around 1 to a few through at that exact moment. When
it sounds like there's music in here.
As the positronium enters the interaction chamber, the antiproton beam needs to be fired through at that exact moment. When done correctly, around 3 million antiprotons or so pass through the positronium. If all goes well, around 1 to a few of those antiprotons steal a positron to create an atom of antihydrogen.
Okay, so we've got positrons coming through here, all the way through here, and this is where you capture the positrons.
Yes, we accumulate them.
You accumulate them, and then you shoot them through there, and you make the positronium, and then you shoot that into that chamber, so it mixes with the antiprotons.
Yep.
So cool. It's so cool. Right in here is where they make anti-atoms, anti-hydrogen. They shoot the antiprotons through, and they capture those anti-electrons to form anti-hydrogen, which then travels through here, and then, it will go all the way along there, and they do their experiments. It's absolutely insane. I feel like I should not be in here, but it's so cool.
Now, one question I had after learning all of this is why? I mean, why do this? Because the alpha G experiment can already make 100 antihydrogen atoms in 4 hours using a much simpler process. So why is the G-bar team spending years to build a particle accelerator, a positronium converter, and a way to shoot the antiprotons through this positronium just to make fewer antihydrogen atoms in a slower and more difficult way? Especially when you consider that in 2023, alpha G did its own test to see whether antihydrogen falls up or down. Well, to understand why, we need to understand exactly what it is that alpha G did. Their setup works something like this. Positrons are created by a radioactive source, accumulated, and are then injected. It is that alpha G did. Their setup works something like this. Positrons are created by a radioactive source, accumulated, and are then injected up and trapped. Antiprotons then come in from Elena, are accumulated in a trap, and then also injected in a trap that sits just below the positrons. Next, the two antiparticle clouds are gently merged. This causes some of the antiprotons to capture a positron and form antihydrogen just below the positrons. Next, the two antiparticle clouds are gently merged. This causes some of the antiprotons to capture a positron and form antihydrogen. Now, antihydrogen is neutral, which means that the pinning trap can no longer hold it. So if nothing else was done, the antihydrogen atoms would form, drift off, and within microseconds annihilate at one of the walls. It would all be for nothing.
And this is exactly what happened with the earliest antihydrogen experiments. They couldn't hold on to it. Fortunately, there is a way to trap antihydrogen because it has a small magnetic moment. So a second magnetic trap was engineered around the device which could capture the antihydrogen.
Unfortunately, that trap is pretty weak, so most antihydrogen atoms escape and annihilate. But a few stay. And the idea then is simple. Slowly weaken the magnetic field holding them, and as the trap gets weaker and weaker, anti-atoms start to escape. And if gravity pulls antimatter down, like normal matter, then more atoms should escape holding them, and as the trap gets weaker and weaker, anti-atoms start to escape. And if gravity pulls antimatter down, like normal matter, then more atoms should escape through the bottom than through the top.
So what did they find? Does antimatter fall up or down?
They found that antimatter falls down, so it rules out any exotic theories of anti-gravity. They measured the gravitational acceleration as 75% of normal gravity, plus minus 13%, plus minus 16%, which is possibly consistent with normal gravity, but of course the error bars are huge.
And this is also why G-bar is so important, because their hope is to get the measurement accuracy down to 1%, and ultimately to 1 in 100,000. See, when you